Welcome back. So in our last class, we have started our discussion on our third electrical machine, which will be used in our electric vehicle application. That was our switched reluctance motor. So what was the advantage of this motor compared to the previous one? In induction machine, we have seen that it was running at a non-synchronous speed and it had rotor bars inside the squirrel cage induction machine, and its power factor was and performance was also not good compared to the PMSM. Then we have seen the working of PMSM, where we had an permanent magnet on the rotor circuit. So it was an synchronous machine which will be rotating at the synchronous speed, or the speed of the motor will be equal to 120 F by P. The main limitation of our PMSM was the presence of the permanent magnet on the rotor structure, because of which we were dependent on the rare earth material which are not available in India. So to avoid this permanent magnet, the other option which has gained importance is our switch reluctance motor, where it operates on the reluctance principle. So where an ferromagnetic material always try to align itself along the row reluctance path. So that's what will be used in this motor, and based on the structure over here, so if you see, it does not have any type of winding or conductors on the rotor structure. It is just an single ferromagnetic material or an magnetic substance which can be magnetized upon the application of external magnetic field. So what happens over here, the starter winding, it also has a concentrated starter winding, which is pretty easier compared to the distributed one. So in concentrated winding, so we will have the sending and receiving end together, and when we supply the current, suppose in this way, which is marked in this slide, so we will be establishing a north pole on the top end and south pole on the bottom end, and this does not have any type of conductor, any type of supply arrangement. But the moment the field is created because of the starter supply, so it will induce a magnet in the rotor structure. And why that will be induced? Because the magnetic dipoles which are present inside this ferromagnetic substance, they will align themselves in the direction of external field, and slowly we will develop a magnet over here, and this magnet will try to align itself through the minimum reluctance path. That's what, or it will experience an attracting force, and it will try to attain this aligned position from, suppose this is the initial state, so it will experience force and it will try to align itself. The moment it gets aligned, we will disconnect the supply from this starter pole and we will shift it to the next pole, such that and continuous movement which is shown over here will be obtained, and we will be having the movement of our electric vehicle. Then pole pitch, this is what we have discussed in the last class. So based on the number of rotor poles and starter poles, 360 by n will be our pole pitch, and by replacing the T by appropriate pole number, I can find out the pole pitch distance. Okay, so we generally consider the center point as our reference point. So center point to the center point, that will be my meaning of pole pitch. One pole pitch on the starter side, same on the rotor side of the circuit. We have also understood that the SRM can be having odd number of poles, because, and we have seen in the last slide, the moment one coil is given and supply, it will establish north and south pole together. So we can have odd number of poles, but that is not very popular. Generally we have even pole used in our applications. So in an SRM, the electric angle, we have also understood what is the difference between electrical and mechanical shifts. The mechanical shift is, or mechanical angle, is always 360 degree in one rotation, whereas the electrical angle will be dependent on the number of poles, and in this case how it will be different from the other machines, that's what we will discuss today. Then one electrical cycle will be completed in this machine when the rotor pole moves from an particular aligned non-aligned state to an similar next aligned or unaligned position. Okay, so this is what is the difference, because of which we can have odd number of poles in our SRM. That is, one electrical cycle will be completed. Suppose I mark the position unaligned position. What will be my unaligned position? The case over here, suppose for the example over here, this is my aligned position, whereby north and south pole are placed adjacent to each other on the rotor and the starter side of the circuit. So I say this as aligned position, and the other position which is marked in the dotted line is my unaligned position, where my rotor and starter slots are apart from each other. So if I mark this as my reference point, one electrical cycle will be completed if I come back to this position, that is same unaligned position, to again unaligned position. If I mark the aligned position as the start of my cycle, when I come back to the next aligned position, I will say that I have completed one electrical cycle. So, movement of one rotor pitch will be equal to 360 electrical, or we will be completing one electrical cycle when the rotor pole moves by one pole pitch or one slot distance is covered by the machine. We say that we have completed one electrical cycle. Let us understand by this graph. So, here we have marked this as the aligned position, because S1 and 1, if you see, they are aligned. So, we say this to be 180 degree electrical. Okay. So, that is the electrical position which we generally consider, that when it is aligned we say it is 180 electrical. When it is unaligned, it will be at 0 or 270. That is what we will see. So, over here if you see, it is 270 degrees. Okay. So, here how it is 270 degree electrical, so, or we have shifted by 90 degrees. If you see the difference from the subplot A and B, 90 degree in the electrical angle has been changed. How it is so? So, if you see, it was aligned, now we have come to the unaligned position. Okay. So, when it moves bit further, we will get this empty region aligned across the slot 1, then we will come back to our 360 electrical. Okay. So, when again N2 gets aligned with S1, we will complete one electrical cycle and we will come back to 180 degree electrical, which was our starting point in our discussion. Okay. So, similarly, whether I mark aligned position or unaligned position at the starting point of my cycle, so when I come back to the similar type of position, I will say that I have completed one electrical cycle. Okay. So, here if you see, as I said, this is unaligned position which is marked as 360 degree electrical. The next will be N2 will be aligned with S1 and I will complete one electrical cycle. Okay. So, what is the conclusion from this discussion? When my rotor moves through one pole pitch, or I come back to the same aligned or unaligned position whichever I have marked at the starting point. So, if I come back to the same point by using the next rotor slot, then I say that I have completed one electrical cycle. The starter pole belonging to the same phase will share same electrical shift. Okay. So, now in this discussion we are trying to find out what will be the number of phases in our SRM. Okay. So, how to find the number of phases? For that we will be requiring to find out the electrical shift, okay, or different electrical shifts present inside the machine. Okay. So, if you have observed in our previous discussion, we have only concentrated on N1. Okay. So, if you see the position of other poles also, so as N1 is moving, the relative position of N2, N3, they are also changing. Okay. So, but this factor will remain the same, that the whichever rotor poles are marked, starter poles are marked with the same phase shift, they will always have the same phase shift. Okay. So, what is the meaning of this one? Irrespective of the rotor position, they will have the same electrical phase shift. So, that is what we will see in the next slide. For the starter pole belonging to the other phase, these electrical cycles will be phase shifted. So, what is the meaning of that? Suppose in particular phase, A phase, suppose we have 3-phase machine ABC, which is the popular one. Suppose we have 3-phase machine and A phase has 180 degree electrical at a given point of time, then whichever starter poles which are marked under A phase, they all will be having the same electrical shift at that particular time, that is 180 degree electrical. At the same time, B phase may have 90 or some other electrical shift other than this 180. Okay. So, when I see the C phase, it will also have some other, suppose 300 electrical, some other electrical phase shift. Okay. So, but whichever starter poles are there inside the C phase, all of them will be having 300 electrical. Okay. Now, therefore, the number of torque pulsation, okay, so in one mechanical revolution will be given by S into M by NR. Okay, so this is something which is called as strokes in our IC engine. So, the similar way here we will be having number of torque pulsation, or the number of steps in which my SRM will be completing one mechanical revolution. Okay. So, that will be given by M into NR, where M stands for the number of phases and NR stands for number of rotor poles. If I know the number of phases of SRM and the number of rotor poles, I can calculate the number of strokes in which it will complete one rotation. Okay. that depending on the number of rotor and stator pole, each stator pole will have certain electrical position at a given mechanical rotor position. What is the meaning of that? The moment our rotor changes its position, this electrical shifts. For example, here we have marked 180, 90 and 300. So, this electrical shift will be for a particular rotor position. The moment rotor position changes, suppose I change the rotor position by 10 degrees. Okay. Now, suppose 10-degree movement has been achieved, and so what will be my new electrical phase shifts? So, it will be at 200, it will be at 110, it will be at 320. Okay. So, what is the inference from this example? So, whichever phases or A phase, so if you see whichever slots will be there in the A phase, at this point of time all of them will be having an electrical shift of 200 degrees. All the rotor slots which are stator slot which are present over here, they will be having an electrical shift of 110 degrees. Similarly, whichever stator slot are present with the C phase, they will having an electrical shift of 320 degrees for this particular rotor position which has moved 20 degree ahead from our reference point. Okay. Now, this can be either 180-degree electrical unaligned position where it will be 0, or somewhere between the aligned and unaligned position. So, our entire electrical cycle will be changing from 0 to 360 degrees, and this 0 to 260 degrees will be changing based on the rotor position. That is what is the meaning of this statement. Now, let us understand by seeing an example in this case. Okay. So, here if you see this R1 and N1. Okay. So, here these degrees which are marked inside the structure of the rotor are your mechanical shifts. Okay. So, they always have variation between 0 to 360 degrees if you see irrespective of the number of rotor poles. In our case, how many rotor poles are there? 8 poles are there. How to calculate the mechanical shift? Mechanical degrees are always limited to 360 degrees for one circular path by 8. So, it will be 45 degrees. If you see, each of them are having a shift of 45 degrees from each other. Okay. This is how the mechanical rotor angle shifts are calculated. Similarly, mechanical starter angle shifts. So, if you see, we have 6 number of poles. So, here it is 360 by 6. So, each of them is shifted by 60 degrees. Okay. So, these are your mechanical phase shifted. Okay. So, they are determined from the structure or the number of poles we have on the starter and the rotor of the circuit. Now, the variable one will be our electrical phase shift, which will depend on the rotor position. Okay. So, I hope it is clear for the mechanical rotor angle and the starter angle. So, it is always given by 360 by Ns or Nr based on whether we are calculating the mechanical angle of rotor or the starter circuit. Now, 0 degree electrical. Okay, so here if you see, I have marked this unaligned position as our electrical 0 shift. Okay, then when it moves further and it just starts being aligned, so NR1 is just starting being aligned with NS1. So, if you see, we have covered 90 degree or 1/4 of our electrical cycle. Now, in the next 90 degrees, it will get aligned. Okay, or aligned position is marked as 180 degree electrical, unaligned position is marked as 0 degree electrical or 360 degree electrical. That is end of or starting of my cycle. Whereas at the midpoint, it will be in the aligned condition. Okay. So, now further 90 degrees, the rotor has further moved by 90 degrees and we have got 270 degree electrical. Okay. The next position will be your unaligned position. Again, if you see, NR1 has unaligned from NS1 and we have got 360 degree electrical. Okay. So, with this, through this graphics, we have understood what is the meaning of electrical shift for a given mechanical shift. Let us go back and see the entire cycle once again. So, in this case, we have considered an 6 by 8 SRM where 6 poles are there on the starter circuit. So, each mechanical degree will be 360 by 6, 60 degrees. So, if you see, these mechanical angles are marked over here, they are shifted by 60 degrees from each other because of 6 pole structure on the starter side, and on the rotor side we have 360 by 8, 45 degrees is the shift between each of the rotor poles because of 8 poles in the machine. Then that is what is marked over here. Then we have started our electrical cycle by considering the unaligned position at 0 degrees. Okay, so that is the rotor position. If you see, it is marked over here. So let us concentrate on this sub figure where we will be moving the rotor ahead and seeing the electrical shift. Now it is 0 or the starting point. After few movement we will get 90 degrees, then after that 180 where we have perfectly aligned condition, then 270 degrees, and ultimately the end of my one electrical cycle where I have come back to unaligned position. If you see the starting and ending point, so what was my starting point where NR and N2 this unaligned position was there. Now if you see, the rotor has moved ahead by one slot, and now NR1 and NR8 are in the unaligned condition. This is the start of electrical cycle, this is the end of electrical cycle. When my rotor, what is the angle of movement of the rotor? If you see, in this case it has moved by 45 degrees. Okay, that is one rotor pitch has gone ahead. So in my SRM, one rotor pitch movement will be creating one electrical cycle. Okay. So now with this we have understood what is the meaning of electrical phase shift. Now let us calculate what will be the number of phases in the machine. Okay. So for example, 3 phase, 4 phase or 5 phase, how I will identify the number of phases which will be there in our SRM. The inner angles are always your mechanical angles. Okay. Now NR1 is aligned with NS1. Now we are marking this as our initial case where 180-degree electrical is there with us. Now we will try to find out how many phases are there in this particular example. Okay. So the mechanical angles will be 360 by NS and NR, which we have already discussed. So here one mechanical revolution, in that if you see, the number of poles times will be, it will be moving number of pole times faster than the mechanical angle. That is why we will be having many number of electrical cycles in one mechanical revolution. Okay. So here the pole pitch is 45 degrees in our example. In this particular case we have considered 8 rotor poles. So we have 45 degrees as our pole pitch. So when it is moving in the counterclockwise direction, which is marked over here, generally we consider the counterclockwise direction as our positive direction of motion. So when we have counterclockwise movement, so by 45 degrees we will be completing one electrical cycle. Okay. So in this case we are marking this as one particular condition of the rotor or particular position of the rotor. Now we will try to find out the number of phases which will be there in this machine. Okay. Now why it is marked at 180-degree electrical? That is what is our concern, or how this 180 electrical has been determined. So it will be determined from this analytical equation where NS1 electrical, or the electrical position of rotor starter pole number 1, will be given by the NR1 mechanical minus NS1 mechanical, the difference between the mechanical shift of the first rotor pole and first starter pole, into the number of rotor poles plus 180 will be the formula to analytically calculate what will be the electrical shift of particular starter pole. Okay. So how to find out the number of phases in this machine? First step is to write down the mechanical shifts on the starter as well as on the rotor pole, and then the next step will be to assume one of the position as the starting point, or the point at which we will be calculating the number of phases in the machine. Okay. So in this our example we are considering this aligned position as the starting point, or the point at which we will be calculating the number of phases in this machine. Okay. Now we will start finding out what will be the phase shift of electrical phase shift of the first rotor pole, first starter pole. Okay. So why we are calculating the electrical shift of the starter pole, not the rotor pole? Because the excitation will be provided to the starter of the machine. Okay. So the starter of the machine, we have to find out the electrical shifts, and number of discrete electrical shifts will be equal to the number of phases of that machine. So to find out the electrical shift, we have this analytical expression where the first electrical shift of the first starter pole will be equal to the mechanical difference of the mechanical position between the first rotor pole and the first starter pole plus into NR plus 180 degree. Okay. So let us understand by replacing it with actual values. Okay. So, what is my NR1 value over here? Mechanical shift, it is 0 and 0. Okay. So, it will be NR1 mechanical, so that is 0. So, 0 minus NS1 mechanical, because I am trying to find out the electrical shift of first starter pole. So, it is 0. Number of rotor poles in this machine, it is 8 plus 180. So, this will be giving me 180 degree electrical, that is what is written over here. Okay. Now, let us see the phase shift for the next starter pole. Okay. So, here if I write the generalized expression for this one, so it will be counterclockwise stands for your counterclockwise movement. CCW is counterclockwise motion. So, if we have CW, the formula will be bit different, that is what we will see. So, here in this the electrical shift will be limited between 0 and 6. So, that is why we have a generalized formula, we have this. How these two formulas are different from each other? If you see everything is same, just the mechanical number I have to replace it over here and 180. And what is the meaning of this mode function over here? The resultant angle should be limited between 0 to 360 degree. There is no meaning of anything beyond 360, or it simply means that I have completed one cycle and I have gone into the next electrical cycle. Okay. So, suppose what is the meaning of this mode function? Suppose I have 380 from some calculation. Okay. So, if I execute this mode operation, what will happen now? It will become 20 electrical, because it has to remove the whole multiples of 360 degrees, because that means cycles have already been completed. So, 380 from the calculation will be represented as 20 electrical. Okay. Another example, suppose 400, it will be written as 40. Okay. So, that is what is the meaning of this mode function. Okay. So, now let us calculate the electrical phase shift for the remaining starter poles which are marked over here. Suppose this, how we have got 60 over here. Okay. So, for this one, what has to be done? And first NR2 mechanical. Okay. So, because I am finding out the N2 electrical shift. Okay. So, it will be equal to 45 degrees, the electrical shift, mechanical shift of the second rotor pole minus the mechanical shift of the second starter pole, that is 60 degrees into 8 plus 180. Okay. So, if I solve this, I will get minus 15 into 8. So, it will be my 120 minus 120 plus 180. So, the result will be 60 degree electrical, that is what is marked over here. Okay. So, let us repeat this calculation for the third pole. So, suppose the star pole of my starter set. So, what will be the mechanical shift? So, it is third pole is having 90 degree shift. So, here the third pole of the starter is having 120 degree shift. So, minus 120 degrees into 8 plus 180. So, result will be minus 30 into 8 minus 240. So, it will be minus 60 degrees. Again, when I apply this mode function, I want to restrict it between 0 to 360. So, minus 60 is nothing but 300 electrical. Okay. So, that is what is marked over here. Okay. Similarly, when I go for the fourth pole. Okay. So, after that we will have repetition of the electrical shift. So, if you see, so let us just repeat the calculation for the fourth starter pole. For electrical will be equal to, what is the position of this fourth pole? NS4 electrical will be equal to NR4 mechanical. So, NR4 mechanical is 135, NS4 mechanical is 180 into 8 plus 180 degree. So, what will be the result of this one? So, it will be minus 45 into 8. So, 90 into 4. So, it will be minus 360 plus 180. So, it will be equal to 180 electrical, that is what is marked over here. Okay. Similarly, I can repeat it for the next two starter poles, which I will leave that as your takeaway assignment. You can try this and you will see that again you will get an electrical shift of 60 and 300. Okay. So, now what steps we have done to find out the number of phases in this SRM? First, we have calculated the mechanical shift of the rotor side rotor poles. Then we have calculated the mechanical shift of the stator poles. Okay, so how they will be related, that is given by 360 by NR or NS based on which mechanical angle we are trying to find it out. Then we have marked the numbers and we have calculated the respective mechanical shifts. Then after that we are assuming a particular rotor position because the electrical positions will be changing as per the rotor position. So, we will mark one particular condition, and at that point or with that particular rotor position we will try to find out the electrical shift of the stator poles. Okay. So, in our case we have used this formula to calculate the number of electrical shifts of the stator poles. So, now let us see how many discrete electrical shifts are present inside this machine. So, if you see 180-degree electrical, this is same as 180-degree electrical. We have 60-degree electrical, 60-degree electrical, 300 electrical and 300 electrical. Okay. So, we have used this formula to find out the electrical shift of each of the stator poles for a given rotor position. Now, after this marks the last step for our number of phase calculation. So, in this case how many phases will be there in this machine? It will be a 3-phase machine because we have 3 different electrical shifts, that is one discrete electrical shift is 180, other discrete electrical shift is 60 and the third electrical shift is 300. Okay. And I can combine this 300 with this 300 because they are having the same electrical shift. This 60 can be combined over here and this can be combined over here. Okay. So, what is the meaning of this? I have a 3-phase machine where each phase has 2 poles inside it. Okay. So, that is what is the meaning of this one. So, if you see NS1 and NS4, they have the same phase shift or the same electrical shift for the given rotor position. Always, irrespective of the rotor position, I suppose I assume some other position, calculate the electrical shift. These two 1 and 4 will always have the same electrical shift. Okay. So, I can consider that as single phase of the machine. So, a phase can have number of stator poles inside it. So, both of them can be connected to the same phase. Similarly, the other 2 pairs over here and the third pair over here. Okay. So, these are the 3 phases of my SRM and this machine is a 3-phase SRM machine. Okay. So, how I have come to this conclusion, that it is a 3-phase SRM machine for any number of rotor slot. First thing is I have to find out the mechanical shift of the stator poles, then I have to calculate the mechanical shift of the rotor poles, then I have to use the generalized formula to find out the electrical shift for a given rotor position, and the number of discrete electrical phase shift obtained from the calculation will mark the number of different phases of this SRM. Okay. Now, suppose I change the direction of rotation of this machine. Okay. So, if we assume clockwise rotation, what will be changing? Only thing, it will be replaced by plus. Okay. So, that is what should be your understanding, but generalized we consider the counterclockwise direction as the positive direction of rotation. So, that is what we will be considering in this lecture series. So, counterclockwise direction, this formula will be used. For clockwise direction, only the sign will be changing, but everything else will be the same, and the result, whether the motor is moving in the forward direction or in the reverse direction, the number of phases will be the same. That is what will be the logical statement also. So, this is a 3-phase electrical machine, whether it is going in the motoring mode or generating mode, it will always remain as 3-phase machine. Okay. So, we have till now we have seen what are the different types of our SRMs or how they are classified. They are classified based on the pole numbers. We have seen how the number of phases are calculated. Now, let us continue further. In this case, first one is your idealized flux linkage in this case. Okay. So, if you see, the flux linkage is not constant in this machine. Why? Because the rotor will be going through aligned and unaligned position. Obviously, when my air gap is more, my flux linkage will be less because reactance will be more. Okay. So, or the reluctance will be more, or the opposition to establishment of field lines will be more. So, I will get minimum flux when the rotor slot is unaligned. When it is aligned across the stator pole, suppose my rotor pole has aligned across the stator pole, maximum line, because the air gap will be minimum. So, maximum flux lines will be passing through this. So, it will be having a maximum flux linkage. when I will get to this minimum point, any minimum point when it is on the unaligned position. Okay. So, when the rotor and starter poles are unaligned, so I have maximum air gap or maximum reluctance is there or maximum opposition is there. So, flux lines will be less. Okay. So, now how I will excite the machines. Okay. So, in our previous discussion we have found out that it is a 3-phase machine. So, this is my phase 1. So, here if you see the sequence of excitation, phase 1 is excited first, then phase 3 is excited, then phase 2 is excited. Okay. So, whenever this excitation is there, if you see each one of them will be, each phase will be conducting for 120 degrees, that is 360 by 3. We have 3 phases in this machine which we are considering as an example. So, we will be exciting each one of them for 120 degrees. Okay. And the current as we have inductance, because we have coils, they will have some type of inductance, they will not allow the sudden change in the current. So, we will, instead of sudden disconnection of the current after the removal of my voltage excitation, the current will fall gradually because of the inductance. So, we mark this overlap duration where the incoming and outgoing both will be phases will be conducting simultaneously. We call that as commutation duration. Okay. So, this is the conduction duration where only one phase is in conduction, and commutation is the transition period. Okay. So, when one of the phase is turning off and the other phase is turning on. Now, here the contradict is why we have gone from phase 1 to phase 3, why not to phase 2. Okay. So, let us go back to the structure and understand over here. Okay. So, in this case, if you see, now we have, suppose concentrate over on the phase 1. Okay. So, after phase 1 was excited, so what, when it will be excited, when it is in the unaligned position where the rotor will be somewhere here, or with 0 electrical shift I will start the excitation. When I will disconnect the excitation, when it becomes aligned. Okay. So, now no longer the excitation of phase 1 is required. Okay, because it has done its task of pulling the rotor towards it. Okay. So, after that I will disconnect the phase 1. Suppose now I excite the phase 2 first. Okay. So, if I excite the phase 2 first, what will happen now? So, here it will create an counter torque. Okay. So, now in this graph we have seen that after phase 1, phase 3 was excited. Okay. So, why it is so? Let us understand by using this motor which we have considered as example. So, in this case phase 1 is excited first. Okay. So, when phase 1 is excited, what will be the direction of movement? We are considering counterclockwise movement. Okay. So, the rotor will be somewhere over here, unaligned position, and it will start attracting it. So, it will come to this position, then it will start moving towards this because of its inertial force, and after that when it is at the aligned position, and we will remove the supply and we will supply it to some other phase. Suppose I am supplying it to this phase. Okay. Phase 2. Okay. So, what will happen now? Phase 2 will try to drag the rotor in the opposite direction, because that will be providing my minimum reluctance path. So, my rotor slot, so which is present over here, it will be, it has just overtaken. Now, it will try to move in the opposite direction and we will have oscillation of the rotor. Now, if I excite the phase 3, what will happen now? So, this has moved towards, and 3 is just starting getting aligned across the phase 3. So, it will experience force in this direction. So, after phase 1 is excited for 120 degree, or we have an rotor movement of 180 electrical. If I go for phase 3, it will continue the force in the counterclockwise direction. Okay. So, now instead of phase 3, if I go for phase 2, it will produce an clockwise direction of torque, which will make the rotor to oscillate. Okay. So, which is not our requirement. We want the machine to have a continuous movement. So, here we, in our discussion, we are considering counterclockwise as our positive direction of movement. So, how this particular sequence, that is after phase 1, phase 2 has to be excited, has been determined by the condition that continuous torque should be produced in a particular direction of the motion, that is in our case it is counterclockwise direction. So, I will excite the phases in such a way that it generates an attracting torque in the counterclockwise direction. Okay. So, I will never try to generate a clock with torque which will be in the clockwise direction, or else I will have oscillation of the rotor circuit, or there will be jerks in the machine. Okay. So, which is not required or not an desirable condition. So after my phase 1, I will excite phase 3 such that it will produce counterclockwise torque, then it will be given to the phase 2 such that continuous torque is produced, and so on. So now from this discussion it should be clear that we will be selectively turning on different phases. Okay. So now we will be requiring an supply to connect to this machine. Okay. So always we will have a DC voltage source. Now that has to be converted by using some power lines converter, so that my particular sequence of excitation has been given to the machine and it starts rotating. Okay. The flux linkage is produced when and particular coil is excited, because on the stator side only we have the supply, rotor does not have any type of supply, and we have also understood why there will be an variation in the flux lines. Because of the variation, the inductance will also be changing. Okay. The inductance will be proportional to the number of fluxes. If the flux is more, the inductance value will be more. If flux line is less, so inductance will be less. So from the first subplot which we have seen in the last slide, so that's what is given over here. So it will be having an variable flux linkage based on the rotor position. Okay. Due to this silence in nature, our phase inductance in the SRM will be dependent on the rotor position, whether it is aligned or unaligned. Based on that, my phase inductance value will be changing. So that's why if you see, we have written an L theta value, because this inductance is now an function of my rotor position. If I replace this lambda value by its corresponding L theta, that is by variable inductance value, into the current Li. So and I differentiate, now we have two variables, so we will go for by part differentiation and we will get two terms. And similarly with the mathematical manipulation, that is we have multiplied with d theta and divided with d theta. Then we have replaced by d theta by dt as omega. In our omega is nothing but our angular frequency. Then the power procession in this equation, from the same analysis we are carrying forward, we have multiplied both sides with the current terms, so that we get this product of I and B, which will be my power which is generated in the SRM. Okay. And with the subsequent analysis and simplification as shown over here, so I will find out that the torque of generated by this SRM will be given by half I square into L d theta by L theta by d theta. Okay. So this will be the torque expression. So based on my torque requirement, I have to change the current value. Okay. So it is having a quadratic relation with the current flowing through the machine. Now SRM machine, how it will be supplied. Okay. So if you see, the supply to the SRM will be a DC supply. Okay. So where we will be repeatedly turning it on and off. So why it will be repeatedly turning on and off? So that depends on the type or the control methods which is used in this case. So we will try to maintain an I reference. From where we will get this I reference? From the last slide we have seen the torque and the current relation. From the given torque set part, we will be having an particular value of current, and this is called as your hysteresis current control, where we will have an upper band and lower band, and we will try to maintain the current within. So when the current is touching the lower part or our lower band, we are turning on the DC supply, or we are connecting an positive supply to it, so that it gets charged. The moment it touches the peak current value, we disconnect it and connect to 0, or the other option is we can connect to minus VDC also. Okay. So if we go for connecting it to minus VDC, we will be going into a hard switching mode of operation. If we connect it to 0, or we will be just bypassing the coil which was excited, then we will go into soft switching mode of operation. So these are the two different modes in which the transition from the peak value of current to the value point of the current will be taken care. That is either by applying minus VDC or 0. Okay. Now till now we were concentrating on the motoring mode. Similarly, we can go into the generating mode, or regeneration also can be done by using the SRM. It can also operate in the 4 quadrants. Okay. So this will be my flux linkage with respect to the rotor position. Now voltage with respect to the rotor position. Okay. So from 0 to 180 it is always on the motoring mode, and from 180 to 360 it will be in the generating mode. Okay. Similarly, the torque is shown over here. Then the 4 modes of operation of our machine. So it is standard. The same classification can be done for induction machine or PMSM based on the direction of your torque and the speed of the motor. Okay, the forward motoring, forward generating, backward motoring and backward generation. Okay, the forward motoring is nothing but the normal direction of motor movement. Okay, suppose I have covered the required distance, now I want to stop the vehicle, I have some excess energy, I can go for the generation modes that I can call as regeneration. Then reverse motoring, so when I want to move the vehicle in the backward direction, or I have applied reverse gear, I will go into the backward motoring, and I have moved to the required distance in the backward direction, I can again go for generation of the excess power or recovery of the excess power, and I can go for reverse generation also. Okay, so these are the 4 modes of operation in which my SRM can be operated. Then coming to the converter, we will just see as a small example. So here, if we are using this SRM for other type of applications and we have AC supply, then this part of the circuit will be present. For our electrical vehicle applications, we always have a battery bank over here. So it starts from this point of the circuit, we have a battery bank, and the modes of operations which we have just now discussed. So whether we are applying 0 state for discharging the inductor, or we are applying minus VDC to discharge the inductor, that defines which mode of operation is there, hard switching or soft switching. So we will come back to this hard switching and soft switching in the next slide. So before that, let us see why it is called as asymmetrical bridge converter. Okay, so here it is asymmetrical bridge converter because it has 2 switching devices and 2 diodes. Okay, each phase has 2 switching device and 2 diodes. So that's why we call that as asymmetrical bridge converter, because one leg is containing the switching device and other leg is containing the diodes. Okay, so now let us see what will be the modes of operation of this converter. When I want to connect it to the supply, I will turn on T1 and T2. So it will be creating at this point will be connected to the top bus, this point will be connected to the bottom bus, and my inductor will be supplied or connected to the DC link voltage, and it will be charging. Now how I apply the discharging state, that will define whether I am going for hard switching mode or soft switching mode of operation. Okay, if I remove, suppose I have moved the current towards the peak of the band, okay, which we have also seen. Okay, so now I want to move it down. So I have 2 options. First is to apply 0 voltage, second is to apply minus VDC or negative of the DC link voltage. So how I will apply minus VDC? If I remove the pulse from T1 and T2, now inductor was having current in this direction, because in the previous case T1 and T2 was on, so it was charging. So it will try to maintain the current in that direction. Okay, and I have removed the pulse from T1 and T2. So how the current will be flowing? So it will flow through the DC link, to the diode, and back to the inductor. Okay, so if you see now, my inductor has to drive minus VDC. So if I remove the pulse from both T1 and T2, I will go into hard switching mode of operation, where I will apply minus VDC. Now suppose instead of removing the pulse from both T1 and T2, my inductor has charged to the peak value. Now I will just remove the pulse from T2, suppose. Okay, so now the current was flowing in this way. So T1 is having the pulse, so it will just circulate in this loop. And what was the voltage seen by the inductor? If we neglect the onset drop of the devices, it will be 0. So it will be having a soft switching mode of operation. Okay, so how I will go into hard switching mode of operation? When I turn on T1 and T2 for connecting it to the DC voltage or for charging it, and I remove both the pulse of T1 and T2, I go into switching mode of operation. For discharging, if I remove the pulse from any one of this switch and I maintain the pulse of the other switch, so the inductor will just circulate the current, or it will just free will, and it will experience 0 voltage, and we say that to be a soft switching mode of operation. Okay, so let us see this as an example. So here in this case, if you see, we have turned on both S1 and S2. So it is having a charging mode, or it is storing the energy. Then I have turned on both the switches. So if I apply the KVL or the voltage to be generated by the inductor, I will see that it will be equal to minus VDC. And in the third case, if you see, I have just removed the pulse from T2 in this example. So this will be circulating, the current will be circulating through this path, and we will have soft switching mode of operation. Okay. So, this state is common for both hard and soft switching. If I apply stage 1 and 2, I will go into hard switching mode. If I apply state 1 and 3, I will go into soft switching mode of operation. That so this is what is shown over here. So, here when both the switches are on, the voltage applied across the phase is plus VDC. When both the switches are off, it will be equal to minus VDC. When one switch is on and one diode is connecting, it will be equal to 0. So, if I want to operate this converter in hard switching mode, I will select these two states. If I want to go for hard switching mode, if I want to go into soft switching mode, I will select 1 and 3 and I will go into soft switching mode. Okay. The advantage and demerit wise, which one will be more advantageous? Obviously, soft switching mode will be more advantageous because the switching frequency of the converter will be less, because the inductor will be discharging at a slower rate. So, my frequency will be less or losses will be less in this case, whereas in the hard switching mode the current will be repeatedly switching between plus and minus band. So, we will be having a higher switching frequency and switching losses will be higher. So, the recommended mode of operation of this converter is soft switching mode of operation, and similarly we can have various other types of converters to feed our SRM. Just to give an example how the converter is different from our conventional inverters which will be used for PMSM and induction machine, we have seen this example. In this case, we have understood that our asymmetrical bridge or the SRM will be fed from an asymmetrical bridge type of converter or any such derivatives, where and DC voltage will be applied across the inductor. So, SRM will be supplied with a DC source, whereas our induction machine and PMSM are supplied with AC source. Okay. So, with this part we will stop with our lecture series. My part of the lecture series has been completed till this point. So, in this entire course of 25 lectures, what we have seen is we have covered the power electronics aspect and the drives aspect of this course. So, we have seen the drives part and the power electronics part, and from this point we will be continuing with our control system. Then we will be going into the grid integration and the challenges of the grid integration. So, to summarize our discussion, first we have started with our drives, switches, then we have gone into the converters which will be used inside a charger, then we have seen what will be the converter used on board, then we have gone into our electrical machines, their performance, their control, and brief working of each of these machines. So, we will stop at this point. We will continue with the next module from our next lecture. Thank you.